Niels Bohr was born in Denmark, and he's considered one of the greatest minds in science. He made a very huge mental leap in adding definition to the atomic theory of the day. He followed Rutherford, and so Rutherford discovered the nucleus and the protons comprising it and the electrons revolving around the nucleus. Niels Bohr adds definition to the electrons and that they exist in different energy levels, which he calls principal energy levels. I have a picture here of Niels Bohr as a young man. He was a good soccer player. His father was a professor at the University of Copenhagen, and he was a very good student. He also lived during Nazi occupation, and so he was instrumental in bringing physicists out of Germany. And then he himself had to flee out of Denmark to go into Sweden, and then there was a heroic escape from Sweden to the UK, where he joined the Chadwick Labs. He is seen here with Albert Einstein. Later in his life, he's involved with the Manhattan Project. I already mentioned that one of the key things that struck Bohr was that each element had a unique line spectrum. And so let's first of all talk about the fact that when we actually do the experiment of flaming different elements, we see different colors. And when we look at them through spectroscopes, we actually see distinct lines. Right now, we have a picture here of neon, and we're used to neon being red when it glows, when it's electrified. And this is the mercury goes blue. And you would also see that hydrogen is pink when it is excited. The gas is excited. If we'd look through a spectroscope at white light, white has every wavelength present. But if you look through these gas cylinders, you see the hydrogen spectrum only has 3 lines, the helium spectrum has 5, and neon has a lot of lines. That's just in the visible spectrum. There are a lot more lines if you look in the infrared or the ultraviolet. Niels Bohr considered this, and he worked mathematically to assign these wavelengths to the associated energies, and from that he figured out that electrons are existing in different energy levels and they're jumping when energy is added. When we do an experiment, we are going to heat the elements, and this causes the electrons to absorb particular amounts of energy, and when they do, they emit light on the descent. The hydrogen atom has 1 electron in the first energy level. N equals 1, meaning the lowest energy level. So there are quite a few options available to this electron. It can jump up to the second, and then it could drop back down to 1. And I'm doing a wavy line to show the photon of light that's emitted as the electron is relaxed back to the lower energy state. And then this electron could jump up to 3, but then it might not come all the way back down to 1. That's one possibility, but another would be that it could jump down to the second. And then maybe this second one could jump up to the 4th and relax to the 3rd. So there are many different possibilities that the single electron could do. It could excite many levels, come down stepwise. It could excite all the way, come all the way back down. We look at all these different options. That would say there are quite a few different light wavelengths that could be emitted. But in the hydrogen spectrum, in the visible range, we only see 3. In particular, what is seen is 3 to 2, 4 to 2, and 5 to 2. These correspond in the visible region to a red, a blue-green, and a violet light. I want to work through a virtual lab that Mike Jones, who's a teacher in North Carolina, developed that I've used for years. It's a wonderful thing. Because most of us don't have high-end spectroscopes, this lab wouldn't be possible for us, but we're going to do a virtual lab here. So this is an experiment, and we're going to try to reproduce what Bohr did. So this is a spectroscope, and it will allow us to measure the wavelengths of light coming out of the excited hydrogen gas. So a high voltage is applied to a cylinder that's filled with gas, hydrogen gas, and it emits a light. And here's the eyepiece that you would look through. And then there's what's called a diffraction grating. So here's the grating, and it splits the light into its components, mainly by bending them through a narrow slit. Light has that property that it breaks up into Roy G. Biv as it goes through a narrow slit. And this is a close-up of the measurement scale. And then here's the superposition of the 3 hydrogen wavelengths. And if we would literally measure these, we would measure them, and I did this earlier. We'd see one at 434 nanometers, 486 nanometers, and 657 nanometers. That's 657, 486, and 434. There are other wavelengths, but we don't see them in the visible region. Okay, now we're going to predict what the jumps are that correspond to these particular wavelengths being emitted. So to figure that out, we have to figure the probable energy levels from which they would derive. So Bohr used an equation like this. The energy is related to this Rydberg constant, 1 over the principal energy level, and this is like 1, 2, 3, 4, 5, 6, 7, the 7 principal energy levels in the atom. And this is the value of the big R, 2.18 times 10 to the minus 18th joules. And you'd figure out for each energy level what the energy calculation is. Okay, then we look at the energy change between the 2 levels, and then we relate this to wavelength, because energy can be related to wavelength, and that's the relationship that's new to you. And it ultimately lets us calculate the wavelength of light that would be associated with an energy change like that. I'm just giving you a view of the math, but I'm going to show you a simplified form. I've simplified the equations and merged them to this one. The wavelength of light emitted would be, I combined those 3 different constants into one, and then it's going to be divided by, these are the 2 energy levels involved. The higher one minus the lower one, but it's reciprocal, that squared is the form. Okay, now some of these jumps wouldn't make any sense, like 1 to 1 doesn't make sense, and 2 to 2 doesn't make sense, and 3 to 3, and so on down the line, right? So those aren't jumps. And so all of this is shaded out too, because we wouldn't be jumping up. We're doing the light emission happens on the way down. Okay? So this triangular area wouldn't make sense for jumping. So if the electron exists at n equals 2, the second energy level, and drops down to n equals 1, if I run through these calculations and I say this number divided by 2 squared, 1 over 2 squared, minus 1 over 1 squared, when I do that, I get a wavelength of 121 nanometers. And I could run some of these other numbers. I got 103, I got 97. Okay, the ones that really turned out to match the 3 that are seen in the visible are these 3. 3 to 2 gives you 657. 4 to 2 gives you 487. And 5 to 2 gives you 434. So Bohr mathematically was able to correlate wavelengths observed to energy levels using those standard energy equations that de Broglie developed. And Rydberg, I should give him credit too. So that's the basic idea. I wanted you to see it. And now let's talk about how this fell short of being a working model. Basically, the Bohr model only worked for hydrogen. The more complicated atoms could not stand up mathematically. So we say Bohr was the first of the quantum model guys. He himself recognized that this was a limited view. However, he did the very important thing of saying that energy was quantized, that it was specific values and not continuous, and this is the foundation of the quantum model, which we talk about in the next video.